You want to model the thoughts and the words of someone. You have access to the words, but you don't have access to the thoughts, therefore they're latent. Thoughts can be bad and good, same for the words. You encode this with numbers, then you see the thoughts are a Bernoulli distribution, same as for the words, and they take parameters. Now you have data, you listen to the words of someone, and you know whether they're bad or good, but you don't know their thoughts. And you want to infer the feeder parameters. You have a maximum likelihood under missing data. Welcome to the expectation maximization algorithm. Hi, welcome to a new video. Today we want to look at the expectation maximization algorithm. I will derive the most important equations for our example of the words, our Bernoulli model. In the intro we've seen that the main point is that we don't have data for the latent variable. So if you listen to someone, you don't know what's going on in their head. So you don't know what is causing the words that he is speaking. And you only can know about the words that is speaking, so you might have to infer about the thoughts. But our task here is to infer the parameters that are causing the relation between the thoughts and the words. So let's look at this again. We are given data, and the data looks as following. So we have a data set, and the data set consists of tuples because we have two random variables in our directed graphical model. And we know the 0th word someone says, but we don't know the thought that is cursing this word. And the same is true, we know the first word that someone is saying, but we don't know the thought that is related to it. All the way to the last word, the n-1th word, and the respective thought. So actually what we have, we only have data on the words. I mean, actually only data on the words. I mean, it makes sense. That's the only thing that we have access to, as it is the observed variable. So the data is just W0, W1, all the way to W capital N minus 1. And you know, for the maximum likelihood estimate, we have to define the likelihood of our data. And let's try to get this here. So the MLE requires likelihood of data. But we can't plug in our data into our model because our model is a probability density function or probability mass function of T and W, but we only have W. And the solution here is that we work in terms of the marginal likelihood. So the marginal likelihood is that we only calculate the likelihood of the values that we can observe. So we have to find the likelihood using P of W, which is the marginal. Let's get there. Let's call this the marginal likelihood. And we use the same letter as for the full likelihood, which is the capital L of our data set, given the parameter vector theta. And the parameter vector theta is just a shorthand notation for the parameter theta t, so the Bernoulli parameter for the thoughts, then the vector of Bernoulli parameters for the words, transpose because we want to align them in one vector, and then transpose. So it has 3 components in our case. And for this, we would use, in case of our IID samples that we, of course, have, as always, in our maximum likelihood estimate, we take the product over all the samples that we have and say that P of W is the W observation. But now we said that we only have a P of T and W model, and we need a P of W. And the way to do this is, of course, we have to marginalize our joint. So this would work as following. And P of W is the summation over all possible states that our latent variable can take of the joint given as P of T and W. And in our case, this would then look as follows. So when we look at the Bernoulli model, we have a P of W, which would be the summation from small t 0 to 1 of P of capital T is small t, and W. But to be more general, I will resort to this way of writing it down. And the big disclaimer up front, the EM algorithm that we are going to derive will not work. Wow, that's crazy. But I think it's a really interesting example to look at the Bernoulli model, as it still provides us with the equations that are relevant for EM, but not necessarily has to do with all the hard math that we need in following examples. So disclaimer, the EM does not work for the Bernoulli model. So, and more details on why it does not work are listed in the video description. But anyways, let us continue. Okay, so now we have an expression for our marginal. So let's put this down. So we have the likelihood of our data under the parameter vector theta is the product over all the samples that we have, and then we have the marginalization procedure, and then we plug in the values or the words that we observed of our speaker. Similar to other maximum likelihood estimates, we prefer to work in the log likelihood environment. So let's derive the marginal log likelihood. And for this, we will just use the lowercase d, and we apply the logarithm operator to our likelihood, or to our marginal likelihood. And if we do this, then the logarithm turns the product into a sum. So we get the sum from I0 to capital N-1 of the logarithm of the marginalized, or of the marginal. And this is actually the first problem that we will encounter here. So we solved the problem with the latent variables by introducing the marginal, but now we have a really complex expression because we have the logarithm of a sum. And in the first place, this might not seem as hard to you as it will end up to be, but the problem here that it induces difficulties when we maximize this later on. Because remember, for the maximum likelihood estimate, we have to maximize the likelihood. So the problem here is hard to optimize later on. So we kind of want to circumvent this, and the easiest would be to kind of move the logarithm into the sum. So if there is a way to get this logarithm into the sum, this would be extremely beneficial. And let's phrase the question as following. So how to get the log into the second sum? And for this, let us look at the expression that we found for the marginal a little more closer. So let me again write this down. So we found the marginal to be the summation of all t of p of t and w given wi. And this might remind you of something. So if we have the summation over all possible states of something, this is kind of like an expectation, right? So we would be doing some sort of an expectation, but we don't know what we're taking the expectation over. And now we will introduce a trick. So we will multiply with an artificial 1. So we have a summation over all t. And here I will introduce another distribution. Let's talk about this in a second. And I call this distribution q of t. And I will multiply it with 1. So I will multiply with q of t over q of t, which is just like not changing the expression at all. And we get the following. And then we divide this by q of t. So this would cancel out, but we added it on purpose. And now, if you look at the expression of the summation over t times q of t, then you see this is nothing else than an expectation. But let us note down again what this q of t is. So let's say we have another distribution over t, the q of t. And this is like giving us access to more information on the latent variable. And in case you're familiar with it, this is similar to importance sampling, where you would also introduce this kind of trick. I mean, it's not necessarily for what we're doing here, but just to give the reference to those who are familiar with this strategy. Okay, but anyways, now we see that this is like an expectation. So kind of note this down. This is the expectation of t distributed according to q of t over, and then the expression p of t, w is wi, divided by q of t. Great. So we got a replacement representation for the summation term. Okay, let's note this down. Okay, let's close this interlude bracket here. And we get for our log likelihood of the data, given the parameter directive theta, we have the summation from I is 0 to capital N minus 1 over the logarithm of the expectation of t distributed according to q of t of the fraction of t, and w is wi, over q of t. And now we are still in the situation that we have our logarithm out here. And it would be extremely nice to have the logarithm inside of this expectation. But we can't just move the logarithm inside of the expectation, since the logarithm is a nonlinear operator. But here's another trick. And the way to do this is to take usage of Jensen's inequality. Okay, a lot of new concepts here, but this one is fairly simple. And the inequality is given as follows. The logarithm of the expectation over something is bounded, and this is like an upper bound, or is smaller or equal to the expectation of the logarithm of what was inside of the expectation before. Great. And this moves our logarithm inside of the expectation. And also let us note this down. This is some sort of an upper bound. And the upper bound is totally fine, because recall later on we want to maximize our log likelihood or our marginal likelihood. And then the upper bound works totally fine for us, because we can still find the same maxima. And let's write this down. Okay, because we maximize later on. Anyways. Okay, close the bracket for this interlude. And then we finally moved our logarithm inside of our expression. And surely we have to use some sort of our inequality signs. And then we get the summation from I0 to capital N minus 1 over the expectation of t distributed according to q of t of, and here we have the logarithm of first p of t, and w is our observation, and we divide by q of t, closing brackets, closing expectation. Fantastic. Okay, and now we can go back from expectation to the definition of the expectation, because early on we used the trick that the summation over t led us to an expectation, and now we can go back to the summation over t. So we have the summation over I0 to capital N minus 1, then the summation over all t, and then of course we have to get back our distribution q of t and have the logarithm of what we had inside of the expectation operator, p of t, and w is wi, over q of t, and then closing brackets for the logarithm. And keep in mind that this inequality still holds. So when I used the equal sign here, I meant that the right-hand side is equal to this, but it's still like an upper estimate for our log likelihood. So maybe let's note this down. Still an upper estimate. Okay, for completion, let us now spit out a logarithm. We know the logarithm of a quotient is nothing else than the logarithm of the numerator minus the logarithm of the denominator. So we have I is 0 to capital N minus 1, then the summation over all possible states of the latent variable, then Q of t times, in brackets, logarithm of P of t and Wi minus logarithm of Q of t. Nice. But now we have to ask ourselves what this Q of t really is. Earlier we introduced it as a new distribution over t, but now we have to define it. So what is Q of t? But I think the distribution that would make the most sense is the posterior over t. So we use our knowledge of the data set to model t, and we then use this in order to use the trick to get our logarithm inside of the second sum. So let's say maybe as the posterior. So we say Q of t is P of t given our W is Wi. I will just note this here because we will use it inside of the summation then. And that's fantastic. And so we use the posterior. Okay, let's plug this in. Let's say the log marginal likelihood is again given as follows, and it is an upper estimate again, summation from I0 to capital N minus 1, summation over all possible states of t, and then the posterior P of t and given W is Wi times, in brackets, the logarithm of the joint minus the logarithm, and again, of the posterior. And now it is helpful to introduce the parameter to our distributions again to show under which parameters they are given. So because the definition of P is clear, so there's like the combination of our two Bernoullis, but we have to clarify under which parameters they are defined. So let's make this verbose and say we have the summation over all our samples, then the summation over t, then P of t given Wi under the theta vector times, in brackets, the logarithm of the joint under the theta vector minus the logarithm of P of t and, oh sorry, this should be of course be the posterior of the posterior given theta vector. And now it might not be visible at first, but we have some sort of a chicken egg problem right now. Because we used the posterior to estimate our Q of t, and in a later stage, we would now take the maximization of the log marginal likelihood in order to find new theta values. And so let's note this down. This is some sort of a chicken egg problem. So we need theta to model Q of t, and we also need Q of t to update or to let's say to maximize theta and to find the maximum likelihood estimate. Well, this is kind of the problem here. And whenever you encounter chicken egg problems, like some sort of in computer science, you resort to iterative algorithm. So you would first use an theta to model Q of t, then you would maximize for a new theta, and then you would do this over and over and over again until you converge. So the solution would be an iterative algorithm. And the iterative algorithm would look as follows. So you would first guess a theta or a theta 0, let's call this with the index 0, and then use theta and index k at the kth iteration to guess Q of t, and then use q of t to update theta to theta k plus 1 into the next iteration. And these are also the two main steps of our expectation maximization algorithm. This is called the E step because you make an expectation or a guess. And then this is the M step because for this we need a maximization, as we will see later on. In order to make this clear, we have to differentiate between the different iterations of our theta parameters in our expression for the upper bound for the marginal log likelihood. And this in end will also turn out that our marginal likelihood will take not only one theta vector, but two theta vector, the one at the kth iteration and the one at the k plus 1 iteration. So let's note this down. So we have a marginal log likelihood of the data set given an theta vector at the kth iteration and a theta vector at the k plus 1 iteration. And we had the upper bound of the summation from I0 to capital N minus 1 over all possible states. Then we had the posterior, the q of t, which we estimated with the theta k. So the posterior of t, given that the words are the words that we observed, under theta k times, and then in brackets the logarithm of the joint under the new parameter. So because that's what we want to maximize later on. And then minus the logarithm of the posterior again. So the logarithm of p given wi under the old parameters. And then we can define our optimization or the maximization procedure as follows, that we say that theta k plus 1, and I will call this k plus 1 star. And in order to make the notation later on a little bit easier, I will actually remove the star and I will just call this the k plus 1. And instead of having the k plus 1 here in the argument, I will just call it the theta vector. Because in the estimate that we do, this is kind of fixed because this is what we got from the last iteration. But this is our variable in here, which we want to maximize over. So I will remove the upper index k plus 1 in this case because that's the main expression in here. And then we see that theta k plus 1 is given as the arc maximum over all possible thetas of our upper bound of the log likelihood. And by looking at this, we can see another simplification that is possible in here. Because we have some sort of like an additive term, so I forgot the second bracket here. We have this additive term with the logarithm of the joint minus the logarithm of the posterior. Whereas the joint is given by our new theta and the posterior is given by our old theta. And what would happen here is that we multiply the posterior with the negative log posterior. And in terms of our maximization, when we then later on take the derivative, this is a constant. So let's note this down. This here is constant with respect to theta. I hope this makes sense because it uses the old estimate of the theta. It is constant with respect to the new theta that we want to find. And by this, we can also just ignore it in the expectation step. And it would be wrong to still call it an L, and we use a Q, and Q is defined over the data set, and it takes the same arguments, but it ignores this term because we don't need it for the maximization. And we also take an equal sign here because we already define it as the upper estimate. And then it's I from 0 to capital N minus 1 over all possible states of t, then of our posterior given the old parameter, and then we multiply it with the logarithm of the joint under the new parameters. Fantastic. And then we can equally define the theta k at the next step as the arc maximum over all thetas of this Q function. And nice. And I also want to introduce some naming here. And usually what we have here, like the posterior over the latent variable, is called, with the old parameter, is called the responsibility. And we will see this again once we use the expectation maximization for mixture distribution. And it's called like this in mixture distributions. So for mixture distribution, because recall in a mixture distribution, you would have a latent class variable and a non-latent component variable or an observed component variable. And here we would call it the responsibility. Okay, based on this, we can then fully define the expectation maximization algorithm as following. And first, we randomly initialize theta 0, so the first guess of our theta, of our parameter vector, and then we would iterate until convergence over by first calculate the responsibilities. And here we use the format of the algorithm, which is most used in the mixture models. And we call the responsibilities row. And this is the responsibility that the ith sample belongs to the teeth class. And we will see this in a short. So this is nothing else than the posterior that t is a small t, given that w is wi under the old parameters. I think this is the most important fact here, under the old parameters. And then we update the parameters by maximization. And for this we get theta to the k plus 1 is nothing else as the arc maximum over all possible thetas, and given over the expression I0 to capital N minus 1. This is in essence, this is our Q, and over all t's. And here I will be more verbose. I will do t element capital T, and by this I mean all possible states that our latent variable can take. Think of the Bernoulli model of good and bad. So a t that can be both 0 and 1. But as the Bernoulli model does not work with the EM algorithm, this is like all the classes that we have in mixture distributions. And here we would then have our responsibilities that we calculated earlier, and multiply it with the logarithm of the joint, that capital T is small t and capital W is the ith W observation under the new parameters. And if we maximize this, then we get our new iteration, and over and over and over, and we will see we will converge for mixture distribution. Again, doesn't work for Bernoulli model, and we can find the maximum likelihood estimate under missing data. So let's also note this down. So theta star as the limit process for a k to infinity of theta to the k is the maximum likelihood estimate under missing data. And surely one remark, this is not necessarily unique because the EM algorithm hardly depends on the random initialization, but it's a nice thing to think about it, that in the end we get the one maximum likelihood estimate under missing data. Okay, that was a long video with a really detailed derivation. Please feel free to also write a comment if something was unclear. And still, I hope you enjoyed the video, and maybe the EM becomes more clear if you look at an example, for instance, with the Gaussian mixture model. Anyways, thanks for watching. Here you see similar videos. See you next time.